Okay, so welcome to this introduction to BaRatin. Today, I will start with a presentation of the principles of the method and the way it is implemented in the BaRatinAGE software. Then at the end of the webinar, when for those of you who managed to install the software, you will be able to follow my demonstration of the software using the same data. And those data sets will be made available by Ben in the chat of the Zoom session. So I am Jérôme Lecause. I'm a hydraulician, a researcher in the river hydraulics group here in France at INRAE, a French governmental research institute in France. And I will be helped by Ben Renard, who will be able to answer your questions in the chat. And he will stop me in case there is something to explain, something unclear. So feel free to send questions in the chat when something is not clear or you need some explanation during the presentation. And Ben can help with the data too. Ben is actually the brain behind the BaRatin method. So he will be able to answer many questions better than I can. So let's start with this presentation. So I will just start with a reminder of what many of you already know, but the general purpose of stream flow monitoring networks or hydrometry networks is generally to provide the basic data necessary to all hydrological studies, which are the stream flow time series, which means the time series of the river discharges. So usually the stations can cover the full flow regime, what we call the general hydrology stations, but some of them can be only operated for some range of flows, like floods or droughts, for instance. And we can also have some specific purpose stations for instance, for flood warning and forecast, for some projects or water allocation programs, or some legal requirements. This is an example of a region in France showing the network of stations used for flood warning. Okay, there are several types of hydrometric stations. The most classical one, the one that we will address with BaRatin, is similar to this sketch that was given in an old French hydrometry manual, but still up to date. So usually we have an altimetric reference, so usually a staff gauge. Sorry, maybe you cannot see my mouse. Yeah, whoops, sorry. So this kind of staff gauge or benchmarks to give the datum, the zero level of the water levels, of the water stages, what we call the stage. Usually now we have a continuous recording system for water levels, and usually connected to a telemetry system to broadcast the results to the office or to some data servers. But there are still stations around the world where we rely on observers, so people reading the staff gauge every day, for instance. Also, very importantly, downstream of the water level measurement point, we have what we will call the hydraulic controls, which actually determine the stage discharge relation at the station. That will be very important for building the rating curves. We'll see that later on. And to calibrate the rating curve, we usually rely on episodic discharge measurements that people do on an irregular basis, usually for covering a wide range of flow conditions. And that's what we will call gaugings in BaRatin. I know that gauging is not a word used in any English-speaking country, but it's equivalent to discharge measurement in some countries. So we'll call that gaugings in the rest part of the presentation. Okay, so those gaugings or streamflow measurements are not created equal. Actually, they can be now they can be measured using a wide range of measuring techniques, including the traditional current meters, either on a wading rod or suspended to a crane or a truck, like in this picture here. Also, the ADCPs, the hydroacoustic profilers, have been a great revolution in the gauging techniques in the last 30 years, I'd say. Surface velocity methods based on video analysis or radar velocimetry or floats, very old technique, and tracer dilution. So that's not the topic of today, but we have to keep in mind that all these techniques can be the source of calibration data we will use to derive our rating curves. And of course, all those measurements come with different levels of uncertainty. Now, the traditional way of computing and establishing a discharge time series, which is the final output product of the hydrometric stations, is this one. So almost always we never measure the discharge directly. What we measure over time is the water level. So as we saw, the station will measure a water level series or stage time series like this, and we'll have some gaugings, so episodic discharge measurements for different levels of discharges. Those points, those measurements will be used as calibration data to build what we usually call the rating curve, which is a model. It's a stage discharge model that can be used to convert the stages into discharges or streamflow values. And then at the end, we have this discharge time series that is the product of the station. Now, this was the traditional way to go with a single result. And more data producers would like to release the uncertainty around their streamflow series, which means that now we have to work in a probabilistic framework, estimating and propagating all the uncertainties throughout the workflow, and starting from the stage measurements here, the stage series, but also we have to estimate the uncertainties around the calibration data, the gaugings, and estimate the uncertainty of the rating curve to be able to propagate all these uncertainties towards the streamflow series uncertainty. So now we are at the core of the problem we have to address today, which is to estimate the stage discharge rating curve. And what many practitioners are aware of, this requires quite a substantial expert knowledge from the user. That's not just a mere fitting exercise. The first problem is that we usually don't have many gaugings. We have a few calibration data points, and usually they are not aligned perfectly. So there is some scatter due to the measurement uncertainty. and also due to possible rating shifts or rating changes through time. Also, we usually lack gaugings for the extreme flows. Of course, the highest flows, the floods, are difficult to measure, and they are infrequent, so that's difficult to get many calibration data for those high floods. But also for droughts, actually, we can lack data. So the extreme ends of the rating curves are usually difficult to establish comfortably. So the result is that building and maintaining rating curves is difficult, because it's not just fitting a line through data, because then we can have, like here in this red line, we can have a very good fit, but a very hazardous extrapolation to high flows that can be unrealistic from a hydraulic perspective. And on the opposite, sometimes we try to use a hydraulic model to compute the stage discharge relation, but then we have a very good physical basis. But in many occasions, we see that the model is not very well fitted. It can depart from the data we have for medium to low flows typically. So the main idea behind BaRatin, so BaRatin stands for Bayesian rating curves. The main idea behind this method was to reconcile or combine the two sources of information, the data with their uncertainty, and also some expert knowledge, including modeling results, if any, but we don't need a hydraulic model, not always, and to combine those sources of information into a single framework, providing the best rating curve and the best uncertainty estimate we can get from the two sources of uncertainty. And then finally, we also wish to compute and provide the uncertainty on the results, on the final results. Okay, so that method we will see today has been implemented in a software which is a graphical interface, BaRatinAGE, that comes with a user manual and French-English versions for that user manual, and the interface now is available in 25 or 27 languages, and users are welcome to provide new translations in new languages. It's rather easy to do now. You just have to add a column in a text file with the words and sentences translated into your language. So if you wish to add new languages, just contact us or see on the website how to do that. It's rather easy. And then you get the new language is available when you restart the software. You don't have to wait for the next version. Everything is open source, GPL3. So that means that the codes are available and can be modified and used by anyone. I mean the codes of the interface, but also the codes of the solvers, the executables that make the computations behind the interface. We have about 200 users registered, but we no longer ask the users to register. Now the code is fully open source. And those guys here, including Ben and myself, are the many people that contributed or still contribute to the development of the method or the software tools. So many thanks to all of them, of course. Yeah, we have an email address, baratin.dev, that you can use for any question you have on using the software or problems, bug reporting, and so on. You can also ask to be registered to the user list. So there are very few messages on that list, mainly to announce trainings or new versions of the software. And we are very happy that the method and the software have been used by others around the world, by research groups and academics, but also operationally by hydrological services, especially in France with the National Hydrological Service and CNR, and in the USA with NEON, and Argentina with ACUMA. But I'm sure there are others, and you can see examples of research papers using the tool for their own research. So we're very happy of that. Feel free to use it for your own needs, and feel free to contact us to help you. Now, BaRatin in its current form, implemented in BaRatinAGE, is for bijective rating curves only. That means that so far we have not implemented more advanced models or equations to deal with rating shifts, like this example here means rating curves changing after each flood or each erosion or deposition in the riverbed. No hysteresis, not this kind of looped rating curves due to the propagation of a flood wave on a flat channel. That's something that may happen sometimes. No variable backwater when there is a dam or another river or a tidal sea downstream of the station, and that could change the stage discharge relation. So we have methods for all these effects, including seasonal vegetation in the riverbed as well. All these processes that change the stage discharge relation call for more advanced equations, more advanced models than what we have in BaRatinAGE so far in BaRatin. So we have such models in the form of scripts and executables, and we plan to implement them progressively through BaRatinAGE, especially the methods for rating shifts. So that will come in the coming years, I'd say. But so far, you can only compute bijective, stable, unique rating curves using BaRatin. So sorry, you won't be able to do this. Typically, that's an example, a historical example of a rating curve, a very complex rating curve drawn by a French hydrologists in the 50s. Due to erosion and deposition in the riverbed, they had a very complex orbital, what they call orbital rating curve. That's not something you will be able to do with BaRatinAGE. Okay, actually I don't see the chat, so Ben or others, feel free to interrupt me if there are questions or clarifications I have to bring. Now, we come to the most important concepts in the BaRatin method, which is not specific to BaRatin. Actually, it's a very old, very classical concept used by hydrologists to build their rating curves, and that's something we also use in BaRatin. So that's the hydraulic control. You have here the definition from the WMO, the physical properties of a channel which determine the relationship between stage and discharge at a location in the channel. So that's anything, any physical features of the river that have an impact on the relation between stage and discharge, which is exactly what we wish to model with the rating curve. So very classically, we distinguish two types of hydraulic controls or controls. What we call the section controls on the left. So this is side view of an ideal stream or river. You can see that there is a fall, which in hydraulics means that the flow will go through a critical regime, what sometimes people call a choked flow, because it's choked by this critical cross section here due to a fall. And so upstream of the control, we measure a water level that is determined by the discharge and basically by the shape of the critical cross section. So the water level in ideal conditions is nearly horizontal upstream of the cross section, of the controlling cross section, and it's a bit like an emptying bucket. So that's the ideal description, the description of an ideal section control. Upstream of a weir or natural riffles made of gravel, for instance, we'll see that in many cases we can identify such section controls at our hydrometric stations, even when there is no artificial control, and especially for low flows. On the opposite, we have the channel controls on the right. So now you can see that there is no waterfall, and the water line is nearly parallel to the line of the riverbed. And this kind of flow is dominated by the friction of the channel, which means that the stage discharge relation is now determined by the geometry, the shape and size, and the roughness of the channel upstream and downstream of the measuring point, which is a very important point to keep in mind. So this is the main thing to keep in mind: section controls and channel controls. And that's the basic bricks with which we will build our rating curves in BaRatin. Okay, so here are some examples of real section controls at real hydrometric stations. So you see on the left that it can be artificial controls like concrete weirs with notches or nuts, or flat weirs. And on the right, we can see some examples of natural section controls. Like here, for instance, at this station, the water level is measured below the bridges, and for very low flows, like in this picture, actually the water level at the station is determined by the geometry of this cross section here, where there is a fall, there is a critical flow regime, and the control is exerted here. You can imagine that if you dig a hole, you remove some stones from that riffle here. If you wait for long enough, you will be able to see the water level drop a little bit at the station. If you dig a hole upstream or downstream of that cross section, then the water level won't virtually change. So that's what makes this control be the control of the station. Okay, and as for channel controls now, here are some examples from France again, but all rivers around the world are similar. When you have enough discharge, enough water in it, you turn to channel controls with no falls or very, very small ones, and friction dominated regime that can be, of course, perturbated by many things like bridges, vegetation, and so on. But basically, the geometry of the whole channel is influencing the rating curve and the stage discharge relation. Okay, Now, a well-known problem, but worth reminding here, is that usually we have not only one single control active for the whole range of flows at our station. And so this is just a sketch of a typical station, but actually many stations are like this. We can see that depending on the water level and depending on the flow discharge, we can have differing controls that appear, disappear, and in some cases they can combine. We can have several controls that are active at the same time. So in this very simple but very representative example, we could have for very low flows a stage discharge relation that is controlled by this upstream riffle here made of gravels. And if the flow increases, then this first riffle can be submerged and it can be replaced by a higher one located further downstream that can be the second control of the rating curve for medium discharge values. And then after a while, if discharge still increases, all the riffles will disappear and all the falls will disappear, which will end with the channel control. And then the main channel typically will determine the rating curve. And if now we go to flood discharges, to flood conditions, then we can have an overbank flow in a floodplain or floodway. And then we have water flowing in the main channel and in the floodplain or the side arm or the floodway or anything. And then we have two controls that are active simultaneously, the main channel control and the floodplain control usually. In BaRatin, that will be presented in the shape of this matrix. So it's a very simple table, actually. The bad thing is that the upper part of the matrix corresponds to the low flows, and the lowest part of the matrix corresponds to the highest flows. So it's a bit upside down, but anyway, we have different segments. The segments mean a range of stages, and we will study the rating curve segment by segment. And for a given segment or range of stage, we have one or several controls that are active. So to represent this situation that we can see on this sketch, we will tick the green boxes in the matrix this way to tell BaRatin that based on our expert knowledge or assumptions on how our station works, for the lowest flows for segment 1, we have control 1 active, and control 1 is the upstream riffle. Then we have only the downstream riffle that is active. So you see that the box here is now gray, meaning that the upstream riffle is not active anymore. So in other words, all the flow goes controlled by the downstream riffle. And for the third segment, we only have the main channel. And for the highest segment, we have this situation for which both the main channel and the floodplain are flowing. And then we add the two controls. Okay? That wouldn't be a good thing to add the flow over the two riffles. Then we would have nearly twice the right discharge. But when we have this overbank flow in the floodplain, then we have to add the floodplain discharge to the main channel discharge to get the total discharge at our station. Okay. Okay. So this is how basically we built the rating curve model in BaRatin. We don't have to write the equation, but based on this information, BaRatin will be able to write the mathematical equation of the rating curve. And in BaRatin, we simplify the equation of each control to be put in this form, very simple form, as a power function. So discharge Q is a power function of stage H for each control. And so we have three parameters in that equation, what we call the coefficient, A, the offset, B, and the exponent, C. So each of those controls, the four controls here, will be modeled with this kind of equation. So we'll have three parameters for the first control and the first segment of the curve. Then a second equation with different parameters for the second segment and second control. Then the same for the third control and third segment. And for the fourth segment, we'll have a sum, an addition of the third control and the fourth control. So basically, we have three parameters per control. And actually, we also have those K or kappa parameters here, which are what we call the activation stages, which are the water level above which a control becomes active. So that's not always equal to B. In some cases, it is. For instance, for the first control, the activation stage is equal K1 or kappa 1 is equal to B1, because as soon as there is a water level above B1, the control is active. But when we replace a control by another one, like control 2 or control 3, replacing control 1 or control 2, respectively, then kappa is not necessarily equal to B. So we'll have to estimate parameters A, C, and kappa in BaRatin, and B will be computed to keep the rating curve continuous, because the stage discharge relation is expected to be continuous with no gaps or no breaks in the line. So I will come back to this a bit later on. Okay, and very importantly, we have kappa max, or the maximum stage up to which our model is valid. That will be something we'll have to determine. We don't want to compute rating curves far above the maximum water level for which the assumed controls are realistic. For instance, if the station is circumvented by another channel, or if a bridge is submerged, or any event that make the assumptions on the controls wrong, should be considered, and then we should have a kappa max that is realistic and safe. Okay, so we have this equation, Q equal to A H minus B to the power C to estimate, and we could use any values for A, B, C, but you will see that in BaRatin, we will use what we call standard controls just to help the user convey his or her expert knowledge to define the values of the parameters of those controls. So there are many controls you can use in BaRatinAGE. I will just present the main ones here. So we very often use rectangular channel controls, and we make the assumption that the width is at least 5 or 10 times greater than the flow depth. So that's what we call the wide rectangular channel. That's something that allows us to reduce the well-known Manning-Strickler equation into that power equation form. And in this equation, you see that you recognize the A, B, C parameters, but you can see that the coefficient is a bit more complex than a single coefficient. Actually, it's the product of three different terms. So the friction coefficient, that can be expressed as Manning's N or Strickler coefficient. Here it's the Strickler, which is the invert of the Manning's N. The square root of the channel slope, S, and the channel width, BW. So the product of this gives the coefficient A that will be estimated in BaRatin. Then we have B, the offset. B is simply the mean riverbed level at the station, and the exponent 5/3 is what comes from the hydraulic theory. So normally, if we assume that this shape and this type of control applies, then theoretically the exponent value should be very close to 5/3. Okay, so 1.67. Yes, so the coefficient A is all this. Okay, then the second control most useful in BaRatin is the rectangular weir that we use for many natural riffles typically, that can be approximated by a horizontal crested weir like this. So then we again have a hydraulic equation that comes in the form of a power equation, again with an offset B equal to the elevation of the crest of the weir at the station, and in the altimetric reference system we use, and also an exponent that is 1.5 determined by the hydraulic theory again. And then the coefficient A is again a product of several parameters. The discharge coefficient, which is close to 0.4 in that case. Gravity acceleration, nearly constant around the world, very well known. And the width, again, the width of the cross section, the width of the weir, BW. Okay, and that makes coefficient A that we will estimate at the end in BaRatin. Okay, oh yeah, another one for some cases when you have a V-notch or a triangular shaped riffle or weir, you could use this triangular weir equation. Again, it's a polar equation with an offset corresponding to the elevation of the apex of the triangle, an exponent 2.5, and a coefficient that is again a product of several parameters, including a discharge coefficient here, and the angle or half angle of the triangle. Okay, so in BaRatinAGE you will see that you can be helped to design all these kinds of controls. Actually, I'm not sure all of them are useful. I think the orifice is useful. Parabolic weirs and channels can be used in some instances. Triangular channel, I'm not sure it actually exists if it's not made of concrete. But you could also define any values for A, B, C if you wish to use what we call a free control, or something you want to design by yourself. All the others are just convenient tools to help design the rating curve. Now, a very important thing here is that we act as modelers. So the stage discharge rating curve is a model, and we are modeling a complex reality with very simplified hydraulic equations that have been validated for ideal situations, laboratory weirs and flumes and so on. But anyway, for hydrometric purposes, usually it's enough to use very simple hydraulic models to represent more or less complex river systems. For instance, here you have a very simple channel on the left to a very complex braided channel on the right. And when, not for the situation we see on the pictures, but when there is enough water in those three channels, then we will be able to represent all of them by prismatic rectangular channels, very simple ones. But we have to keep in mind that the models, the controls we use in BaRatin are actually representing the reality through this kind of very simplified geometry and parameters. Okay. Now, what we like to do, for instance, to represent a compound channel. So this is a cross-section of a real channel with a main channel and a floodway. We could represent the whole cross-section as a parabola or a rectangle, but usually it's more convenient and more efficient to represent this system using two rectangular channel controls, one for the main channel, one for the floodplain. And we will add the two controls as I showed previously. And the advantage of this is that if we have gaugings to calibrate the parameters of the main channel control, then for floods, we will still have this calibration at hand. Even if we have no gaugings or very few gaugings for overbank flows, then we have a good part of the rating curve, which is already calibrated. So that's a convenient way to model a compound cross-section, to use two cross-sections, two rectangular channels, and to split the real geometry. And you see also that the width and the bed elevation, the offset of the rectangular controls have to fit the average shape and to represent the average cross-sectional area of the actual controls. So this is a modeling. This is modeling. So this is a simplification of the reality, of course. Now for section controls, same problems happen. Sometimes if we have this kind of cross-section for a critical cross-section above a weir, for instance, or a natural river, we will, for high flows like this, we can efficiently represent the whole cross-section by a rectangle that fits the width, elevation, and area of the real cross-section. But if it comes to very low flows, like in this situation, then perhaps the whole water, the whole flow will go through a small notch that was negligible in the previous situation, but now conveys nearly all the water for very low flows. And that obviously we cannot use the previous model for this kind of flows. So for this kind of situation, sometimes we have to consider a low flow control that is different from the medium flow control to represent the small notch or the small holes where the water flows through the critical cross-section. So again, modeling exercise, which needs simplification, but a smart simplification of the reality. Some tips, some tricks for representing real controls. When we have a weir, sometimes it's not perpendicular to the flow. That's this situation, since this is top view seen from the sky. You see that the weir is not perpendicular to the flow direction. And in such a case, the width that counts for modeling the control is the width perpendicular to the local flow velocity. So sometimes the flow changes its direction to be perpendicular to the weir for low flows, and then the full width here is the width you have to consider to model the rating curve for low flows. And for high flows, if the weir is not submerged, sometimes the direction changes and goes parallel to the channel direction. And now the width can be reduced because the width here is the width of the projected line of the weir. Also, we have to we have to add or to sum up all the width of all the weirs we have when we have this kind of combined weir. We have to add B1 plus B2 plus B3 to get the total width of the weir. So there are some tricks like this we have to keep in mind when modeling the stage discharge relation. So now we have seen the most important part in BaRatin, the controls and how to design them. We won't write the equation we get at the end, but BaRatin will use, for instance, this set of equations for this kind of station. We have this example. And now we have 3 parameters per control that we have to estimate. So we have an equation, but now we have to estimate the parameters K, A, and C. So how to do this in practice? That's now when we have to invoke the spirit of Reverend Thomas Bayes, who was among the first to establish what is now called Bayes theorem. And I will explain this with my hands. I won't get into mathematical details, but I will try to explain how the magics works when we calibrate the rating curve using Bayes theory and Bayes theorem. But we are open to using any other spiritual power you could have at your disposal in addition to Reverend Bayes. So I provided some BaRatin training around the world or through video conferences like this, and people can also use other spiritual powers to help. But now we'll stick to Reverend Bayes. So in short, Bayes' theorem provides what we call the posterior distribution of some parameters theta. So the posterior distribution is the probability. You can see this as the probability of the values that can take parameters theta of the rating curve, knowing the observation y. So y, the vector y stands here for the observations, which in our case are the gaugings, the stage discharge measurements. So that's the result of the Bayesian calibration. We get this kind of probabilistic distributions. And we can compute this through this equation. So basically, it says that that posterior distribution is proportional to the product of the likelihood and the prior distribution. The prior distribution of the parameters theta is the distribution that reflects the knowledge we have of the parameter values before we use the observations, the gaugings. So this prior distribution will be based on the expert knowledge or the hydraulic modeling or any source of information we have, except the data we will use in the Bayesian calibration, okay? And that's a very strong rule in Bayesian inference. We never use the calibration data to inform the prior distribution. Otherwise, we would use twice the same information. So the prior distribution, we'll see how we define that in practice in BaRatin. And the likelihood, it can be seen as the probability that the observations appeared or happened for given values of the parameters of the rating curves. So that's something we can compute using the gaugings. So here in the likelihood, you will have the information coming from the gaugings. In the prior distribution, you will have the information coming from your expert knowledge or any source of information but the gaugings. And at the end, we will have the posterior distribution with the some constant here, but we don't really care about these constants. That won't be a problem. Okay, that's the Bayes theorem in short. I won't get into deeper details on that. And now what is important to know or to understand quickly is that when we have this posterior distribution, so here it is represented for two parameters, θ1, θ2. You can imagine it's parameter A and B of a hydraulic control, for instance. We have this density map showing the posterior probability, and we have to sample the values that describe this posterior probability. So for this, we use an MCMC, Markov chains Monte Carlo method, which sample values that represent the posterior distribution. So here on the left, that's some plots you will have in BaRatinAGE if you want to check the values that were sampled for any parameter of the rating curve equation. Here you can see that it's a bit like a random walk, that is not really random actually, but that is following the probability distribution of the parameters. So the higher the posterior probability, the more values you will have in the samples, in the iterations. So basically, that's how the calibration will work. And we will sample a large number of parameter sets that will give a large number of possible rating curves. And we will use these rating curves. Now an example, just to see how it works in practice. If you imagine a very simple situation, here it's a real hydrometric station in France. That is very simple because it's a very high weir, which is never submerged, including during floods. So we can represent the rating curve with a very, very simple model, a single control. And we will see how the Bayesian estimation works for just one parameter, B, which is, remember, B is the average elevation of the crest of the weir here. And let's imagine that we have a very crude, very vague knowledge of the value of B. We have this photograph, we see the staff gauge and we say, okay, B seems to be around 20 centimeters at staff gauge, plus minus 40 centimeters. It's very uncertain. So you will tell this to BaRatin, 0.2 plus minus 0.4, which is the uncertainty of your prior knowledge on B. And it will assume that it corresponds to a Gaussian distribution with mean 0.2 and standard deviation 0.2. So 0.4 is twice the standard deviation, which corresponds to a 95% probability interval. So all the uncertainty results in BaRatinAGE will be expressed as 95% probability levels. So the user will provide this information. The software will compute this distribution, and using the observations, so the gaugings, imagine we have a few gaugings with their uncertainty here. We combine the two sources of information through the Bayes theorem, and then we get this posterior distribution that is sampled here. So what we see here in pink is the distribution of the sampled values through the MCMC process in the posterior distribution. And you see, this is a typical good situation where the posterior distribution is now much tighter, much narrower, with a smaller uncertainty, only plus minus 6 centimeters, and a calibrated value for B, the central value, which is 0.35. And this central value we provide, or the main rating curve we will provide as the most likely rating curve at the end, is what we call the max post result. Max post meaning the parameter value that maximizes the posterior distribution. So the value which corresponds to the peak or the top of the posterior distribution, that will be the value that we will provide as the main result to keep. But of course, a very important thing to keep is also the uncertainty around this parameter and the uncertainty around the rating curve. So that's just to illustrate how the Bayesian inference work for this kind of very simple case. So as we sample 500 or several thousands of parameters, we are able to draw and to plot the same number of rating curves. Sometimes we refer to this as the spaghetti approach, because this bunch of rating curves resembles to spaghetti. And so we have many possible samples. You see also the black rating curve is the max post rating curve, which corresponds to the max post set of parameters. And as we have a large number of results, we can compute statistics on that. And typically, we will compute the 95% credibility intervals. That means that for a given stage here, we will exclude 2.5% of results above and 2.5% of results below to keep the interval where 95% of the rating curves fall in. And then we build what we call the parametric uncertainty interval. This parametric uncertainty is the uncertainty due to the limited knowledge or imperfect calibration of the parameters of the rating curve. And it will display in pink like this in the software. Okay, and again, the max post spaghetti here, or the max post rating curve here. If you have, the idea is that if you want to keep only one rating curve, you will keep this one, but you should remain aware of the uncertainty around that max post rating curve in pink. And we will add another uncertainty term, which is called the remnant uncertainty or structural uncertainty. That's the same. That's an uncertainty component that BaRatin will estimate to explain the remaining deviations between the gaugings and the rating curve. We have some uncertainty around the gaugings that can explain a part of the departures between the points and the curve. We also have this parametric uncertainty around the rating curve that also explains a part of the differences between the gaugings and the curve. But in many cases, we have to add some, or to consider some remnant uncertainty, because there is still some deviations that are not explained by the gauging uncertainty or the rating curve parametric uncertainty. So it's difficult to know precisely what is the error source behind this remnant uncertainty. Very often it is due to limitations in the model assumptions. For instance, if you miss a control in your model, then you will have some differences between the gaugings and the rating curve, and then the remnant uncertainty will increase. Or if you have some rating shifts, for instance, then, and in BaRatin, you will estimate a single rating curve for different situations with rating shifts. Then again, you will need a larger remnant uncertainty to accommodate the gaugings with the rating curve. But usually, we feel more comfortable when the remnant uncertainty is small and smaller than the parametric uncertainty, because we never know exactly what is behind this remnant uncertainty. Okay, so in short, the Bayesian estimation is a convenient method to combine both sources of information from the measurements and from the hydraulic knowledge or the prior information, what we call the prior information. So you can have different interpretations of this process. You can say, okay, we first have a hydraulic-based estimation and we refine it using the measurements. Or you could say that we adjust the rating curve to the data, to the measurements, under hydraulic constraints. Both interpretations are valid. And you'll see that in the software, we can see the prior assumptions in the form of what we call the prior rating curve, which is based only on the prior expert knowledge, not the gaugings. We combine this with the gaugings, and the result is a posterior rating curve with an estimated uncertainty. You see the pink uncertainty and the red total uncertainty, including the remnant uncertainty. Okay, some tricks and tips before we jump to the software. In practice, in the software, you can check some criteria in the results. First, you can check the MCMC traces or samples or realizations of the parameter values. For instance, here for one parameter, A, coefficient A of control 1, we see that we have kind of a random walk, more or less stationary around the same values. So it looks like a good exploration of the distribution. So that's pretty good. Here below, it's not so good because we have trends. Sometimes the samples stick to some regions of the posterior distributions in some lower parts, higher parts. It's not a very good exploration. So maybe we have to increase the number of simulations, or maybe it can also be the sign of some problems in our prior assumptions that are not very consistent with the observations we have. Okay. Also, we have to check if the results are in conflict with our prior assumptions. It's very important to check. For instance, here it's not good. The prior distribution is in blue, does not overlap with the sampled results on the left, the red results. So that means that something is really inconsistent between the prior values we assumed for that coefficient and the results we got after calibration against the gaugings. Okay, a very similar way to see that is to compare the prior rating in blue with the calibrated or posterior rating curve in red. and normally the posterior rating curve should be included in the prior rating curve like this. And the same thing if you look at the parameter distributions, the results, the sampled results in red should be included in the prior distribution with a narrower distribution, which means that the calibration was okay and the prior assumptions are consistent with the observations. Okay, if there is a conflict between the prior and the posterior, then you can check the calculations. That's not very easy to do, but you can check if the MCMC iterations went well, and you can increase the number of simulations. But very often you have to check the values of the priors. There might be something inconsistent in your prior assumptions, but remember, you must not use the results or the gaugings to set the priors. That would be cheating, and that would be some kind of circular thinking, and it could result in underestimated uncertainty because you use several times the same information, whereas the software assumes that there are independent sources of information. Also, you have to review the model and the assumptions you made on the controls and the rating curve equations that might be wrong, and check the gauging. Sometimes we make some mistakes or we underestimate the uncertainties of the gaugings. So that's the kind of verifications you can do to improve the results. Okay, so now we have finished with the explanations on how to estimate the rating curve with its uncertainty. And then in BaRatin, the last step you can go through is to compute the discharge time series or the streamflow time series using a water level time series. And you can define the uncertainty you have on your stage measurements, stage records. And that uncertainty will be combined with the uncertainty of the rating curve to compute the uncertainty of the streamflow time series. So at the end, you will have an uncertainty budget for your streamflow time series, combining the stage uncertainty, that is the discharge uncertainty coming from the stage records uncertainty, and the uncertainty coming from the rating curve. So both the parametric and the remnant of the total uncertainty of the rating curve. So typically, if you want to reduce the yellow one, you would have to improve your stage records or decrease the uncertainty of the stage records, or improve the sensitivity of the controls as well. To reduce the pink uncertainty, we need more information on the parameter values. So we need more gaugings or more detailed prior information on the controls, or both. And to reduce the red parts, so the remnant uncertainty, in many cases, we have to improve the model. So we have to review the number of and types of controls, or to account for rating shifts, or so on. So that's more issues related to the rating curve model. Yeah. So this decomposition of the uncertainty is quite interesting to understand the origin of the uncertainty and how to improve the process if we can. So this is just an example, but we'll see similar example in the software of a rating curve here, computed with the pink and red uncertainty, and the streamflow time series we get at the end for low flows, where you see that the dominant components are the stage uncertainty due to the limited sensitivity of the control, which means that for a small change in water stage, we will have quite a large relative change in discharge. And in red, we have quite a large remnant uncertainty that is due to limited accuracy of the model of the assumed control in BaRatin to represent what happens for low flows. And we have very frequent small rating shifts here that are not well represented by a single rating curve, and that increases the remnant uncertainty because the gaugings are more scattered around the curve. For intermediate flows now, for the same station, we have a different budget. The stage uncertainty now is smaller compared to the total uncertainty. And the pink uncertainty, the parametric uncertainty is larger, which means that we are limited by the gaugings here, the informations from the gaugings. And you can see here we are in this region of the curve, near the break between the low flow control and the high flow control, and we lack gaugings right here, right near the break points. So there is quite a large uncertainty due to this lack of gaugings in this specific region of the flow range. And for high flows, very typically, the parametric uncertainty now is the biggest due to very few gaugings in that region of the flow range. And now the stage uncertainty is totally negligible because the sensitivity is much higher, and 1 or 2 centimeters of stage errors has no influence at all. Okay, so I have finished the main presentation. Now I will provide a demonstration of the software based on 2 examples. But before this, are there some questions on the principles and the implementation of the method? I don't see so many questions in the chat, but if you have some before we do the exercises, you can go now. Yes, I agree with what Daniel is saying. Yeah, of course. Usually we lack gaugings for very low flows and for very high flows due to limitations of the equipment and also limitations in the deployment of the staff. It's hard to be in the field at the right time for very low flows and for very high flows too. But this example is nice because you can also realize that sometimes we lack gaugings in intermediate flow regimes for I don't know for which reason actually, but here it's a site where we have rating shifts, and so it takes some time to get discharge measurements throughout the whole flow range, and sometimes you precisely lack gaugings in some regions where you need them, especially to have a good estimation of the activation stage, so the break point here. So it can also happen. The TP bar files, they will be provided in the chat. Then we'll provide you the bar.zip files that you can open with BaRatinAGE and follow the exercises. Yes, yeah, I agree, Daniel. Yeah, the ADCP is also limited by the flow depth as well. Yeah, but very low flows actually can be very difficult to measure, as you know. we often focus on very high flows, but very small, very low flows or very turbulent flows can be very difficult to measure too. I'd like to know. Yes, yes. I will show you with the software, Swellen. Basically, in the documentation of the software, everything is explained. So how to use the software, but also all the mathematical and theoretical details behind. So we hope that even if someone would like to do a very similar software, all the necessary information should be in the manual. So, and if some information is missing, feel free to tell us. But yeah, about the rating curve equation and everything. Okay, I saw someone raising his or her hands, but I'm not sure. So we stop this. And okay, a question from Slavikas. May I know which values are estimated based on continuity? Yeah, it's parameter B. Prior or posterior B values or both? Actually, it's both, I'd say. But typically the posterior B will be computed by continuity, yes, of the curve. Because prior B are always left blank in the results. We'll see that in the software. I'm not sure we provide the prior Bs. I think they can be computed, but what is sure is that we provide the posterior Bs. Yeah, and in the result, yeah, we don't show the prior curve, the prior distribution of B, because there is no definition of prior B by the user. So we don't provide this. Yes. Yellow. Yes. Okay. Okay. How about iteratively adjust the number? Oh yeah. Yeah, about estimate the question by David is about estimating the number of combination of controls as a response to the structural remnant uncertainty in case you don't have. Yes, that's actually we didn't we choose not to estimate the number and combination of controls. For information, there is the NVE software in Norway. There is they have a Bayesian software similar to BaRatin, and in their method they estimate the number and the type of controls. In BaRatin, we prefer to rely on the expert knowledge of the users because first, usually nearly always the user, the field hydrologist, have enough knowledge on that. And we also fear that in some cases we have not enough gaugings to be sure that we don't miss some controls. So that's why we made that choice. But yes, we could perhaps design some warning based on the structural uncertainty to warn the user that he or she should review their assumptions, yeah, on the controls. But manually, that's what we advise to do. But it's based again on some expert interpretation of the results, but it's not so complex. Yeah. No. And the expert knowledge about the site, in many cases, it's you don't need something very detailed unless you have very few gaugings. If you have very poor knowledge of the controls and one or two gaugings, it will be difficult to build a solid rating curve with limited uncertainty. But for instance, in my experience, I have analyzed many stations I never visited. I just visited on Google Earth or other platforms to get the width and the slope of the channels or sections to see. I got some pictures, some photos of the flows, and in best cases, I can chat with the field hydrologist and get some information from on their station. And in many cases, it's enough to have a nice analysis of the rating curve. In some cases, I have a hydraulic model. I know very well the station and so on, so I can put more precise prior information, but it is not absolutely necessary, especially when you have gaugings. If you have gaugings, it's you can take the information from the gaugings. But for very high flows, for instance, we have to be very careful about the assumptions we make. Yeah, you don't have to unzip the bar.zip files. Actually, you will be able to open them using BaRatinAGE directly. Okay, so another question: what exactly does updating the priors mean in general? Updating. I'm not sure I understand your question. If you mean how we update the prior, it's using the observations. It means applying the Bayes theorem, combining both sources of information into what we call the posterior distribution. So the posterior distribution can be seen as an updated version of the priors using the information from the gaugings. Was this what you meant, Dikas? Not sure. Yes, okay. So that's what we, but I was also speaking about reviewing the priors, which means that you get results that are problematic, and then you wish to review your assumptions, and yet then you design different prior distributions and different models, different controls to get more consistent results. But still not using the calibration results, not using the calibration data to design your priors, which is the Bayesian rule. Okay, Daniel, what is the smallest size of stream that you have? Actually, I think I have it on my computer. I remember a river in the south of France, in the Mediterranean climate region, which was interesting because they had gaugings going over 4 decades, I think, so 4 orders of magnitudes. And I think the smallest discharge was close to 1 liter per second, and the highest was something like 1 cubic meter per second, something like that. So a very wide range, and I think it was also my smallest discharge record. But there is, in a nutshell, there is no discharge limit. But of course, for very small flows, you will need a more detailed description of the controls. Of course, you will have to describe very small controls. That's the only thing, but there is no real limits, or the usual hydraulic limits. If the capillarity effects become important and dominant, then the rating curve won't work as well. But you can go to very low discharges. Is it fine to have multiple prior distribution in advance before the beginning? Actually, we'll see that in the software. The software designs in a way so that you can play with different prior assumptions in the same file, and you can compare the results. We'll see that in a moment. And yeah, it's always good. Personally, I like to start with the simplest prior assumptions possible. And then if I need to increase the complexity of the model, I increase it. But then I can compare, different prior distributions. And with the same model, you can also have different prior distributions and to test that. But the prior distributions should ideally reflect your real knowledge of the parameter values. It is best to be conservative and cautious, and to very often beginners tend to underestimate the uncertainty around their prior values much more often than overestimating the uncertainty. So be careful with that, because if you set very small prior uncertainties, then the calibration is not free to adjust on the data against the data. Okay, Daniel, we monitor a fair bit of tiny forest streams in Sweden. Imagine the influence of small things being important. Yes. Yeah. A small branch, small trunk, anything can, yeah. Okay, good. Okay, I keep an eye on the yeah, so that's something. Oh yeah, that's something that is not implemented yet in BaRatinAGE, the shift times. But that's something we have worked on. We have some tools, some things we plan to implement in future versions of BaRatinAGE to be able to estimate a family of rating curves over several periods due to rating shifts. And also some tools we have developed to detect the times of the rating shifts. I will talk a bit on this at the very end of the seminar. But so far in BaRatinAGE, you can compute several rating curves. We will see that. But there is no detection of the shift times, and the curves are estimated one by one. So I will talk a bit on this later on. Yeah. Okay. So now I will open the BaRatinAGE software and share my screen. So even if you don't have the software installed, you still can follow what I will present. It's not a problem. If you have the software, you can follow the same steps and follow me. So hopefully, where is it? You will see my software here. Yeah. Okay. So we can, whoops. Try to see something in my screen. It's a bit busy now. Whoops. So we can open the first example. So yes, I should rather share. Sorry, I will share the screen, not the software. It will be better. Take care. And this, yeah. So this first example is the exercise file called TP Mercier, MERCIER .bar.zip file. Yes. So yeah, this is just a reminder where you can find the software. And you just have to unzip and paste the directory somewhere where you have the write and read and write rights. And if you double click on BaRatinAGE.jar, it should start the software. In case you have troubles, maybe Ben can help you. Otherwise, feel free to contact us after the seminar and we will help. So we'll play with these two typical cases. So the Mercier River at D610 bridge. It's a case with compound artificial controls, very typical. And another typical case with natural controls, the Ardèche River at Meras BaRatin. Okay, so the first one here. Yes. So the Mercier River is one of our stations actually here. It's a hydrometric station of a research catchment we have near Lyon in the peri-urban catchment of the Izon River, where we study the effect of urbanization on the flows and the water quality. So we have this station for we have operated this station for several decades now, and it's located right here. So it's a small catchment like this, quite rural, and the station is under a bridge. It's a small river, quite a lot of sand. It's that makes some troubles for us. We have to clean it regularly, and we have built this small wall to get a better control of the rating curve. So you can see the staff gauge here. In that steel pipe, we have the water level measuring system. The recorder is above. And we have this combination of rectangular weirs that are always active for the whole range of flows we have observed. So the weir is never submerged, and the fall is never disappears. So the weirs are always active and always determining the rating curve. So the first exercise here is to identify the controls and to summarize the rating curve model we will use. So as I said, we can clearly distinguish the control. It's a very simple case here with this artificial control. We have a notch here for the lowest flows, like in this picture. Then for higher flows, we have this second weir, so in two parts, but at the same elevation. So that will create a second rectangular weir, and a third one, higher one here, for very, very high flows. I don't remember exactly why we designed the weir this way, but I remember we also wanted to prevent the cows and the cattle to walk through the river this way and to disturb our measurements. So maybe it was designed on the obstacle that a normal cow cannot go through. Okay, so here are some useful informations we can use in the software. So I will display this a bit later, but we will use this to build the priors and the rating curve model in BaRatinAGE. So let's go to BaRatinAGE now. So if I go back to the software, I think you can see the software, right? That's what you see now?
Yes.
Yes, okay. So first, before using the software, just to answer one question we had on the manual and documentation. Here, in the help menu here, if you click on help, it will display in your internet navigator, it will display the documentation. of the software. So it's very basic, and it's a tutorial on how to use the software, how the mainframe is organized, what it displays, and how to define the hydraulic configuration, something we will see, how to import the gaugings, what is the remnant error, stage series, how to compute the rating curve, the flow series, and some additional information. And in these explanations, you have some links to more detailed documents. Like here, for instance, this document explains in details that are not necessary to the basic user of the software, but that would be necessary to someone who would like to understand the precise details of the computations. How the rating curve equation is really computed, how the matrix of controls we have seen converts to this equation. Okay, so we hope that everything is in the documentation, so the method is fully reproducible. If you find something that is not clear or not explained, feel free to tell us, and we will include it in the doc. Okay, you can also change the language. I said that. Whoops. Yes. In options, there is a choice for the languages that are currently implemented. Again, feel free to propose translations. Normally, we can accommodate any alphabet. We have Hebrew, Arabic, Russian, Ukrainian, many Armenian alphabet, so Korean, Japanese, Chinese. So it should work with your own language if you don't find it in the list. And I'd like to, yes. Okay, now the software is designed in the logical way from the hydraulic configuration, which is the definition of the priors based on the controls, to the flow series, going through the gaugings, the stage series, the rating curve estimation, and yes, at the end, the computation of the flow series. The same layout is here from top to bottom on the left. And also you have a third way to go through the functions through these menus here. Okay. And I also think you can go this way if you want to add a hydraulic configuration. So add a model, or add gaugings, or add the stage series and so on. So here we have catalogs, what we call catalogs of hydraulic configurations, models, rating curve models, gaugings, and stage series. So here we saw that we have three controls, basically. So we will build a model by adding hydraulic configuration. So you can click right here and then add a hydraulic configuration. You can also do the same thing here by pushing this button here, or through the menu hydraulic configuration add. So we'll do this way. You give any name you want. For instance, I will call this model 3 wheels, just to remind me that I assumed 3 horizontal wheels. 3 horizontal wheels. Okay. I have to tell the number of controls I have in the model, so 3 controls. And then I see the matrix of controls we have seen in the presentation. So remember the real station here. It is made of 3 horizontal wheels that will be active at the same time when the flow will flow over, when the water will flow over the second weir, the first one will still be flowing. So, and that's very important. we want to have the first weir active for the first segment. We want to have the two controls active for the second segment, and the three controls active for the third segment of the rating curve. If you don't tick, sorry, if you don't tick these boxes, then only the upper weir will be active for the highest part of the rating curve, which will be wrong. Okay, so we really need to have all these boxes ticked green. I hope this is clear to everyone, because it's a very important thing. Okay, so the first control. So here in this panel, we will define the three controls. So the first one is the lowest weir, and for each control, we don't have to, but it will help to go through standard controls. So instead of an unknown of free control, where I can define the values of the three parameters and the corresponding uncertainty here, I will be helped in this by defining the type, the nature of control, which is a rectangular weir, and clicking on the prior assistant here, which will open this window that reminds the formula, the equation for a flat weir, a horizontal weir, as we saw in the presentation, typical value of some parameters. So all the parameters that have pre-known values are already set. So in most of the time, you don't have to bother about these parameters. So for a flat weir, we only have to provide the width here, the weir width, and the activation stage, which in this case of adding a new control is equal to offset B. So it's equal to the elevation of the crest of the weir. So getting back to this design of the structure, we can see here that the datum, the staff gauge datum is here. So level 0 is at the bottom of the sketch. And the first weir is 3 centimeters above 0. So that gives us a very precise information on the elevation of the activation stage of that weir, 3 centimeters. And the width is 40 centimeters. Okay. So that's a specific case where we have the design, we can measure precisely an artificial structure. Of course, it's not always the case. Very importantly, remember that in the software, everything is expressed in SI units, so in meters, kilograms, seconds, not in millimeters, centimeters, feet, cubic feet per second, and so on. So everything is in meters. So the width, we said 40 centimeters, so 0.40 meters. The uncertainty, I would have to estimate this, but it includes the measurement uncertainty if I have a topographic survey, but also the differences between the ideal rectangular design and the real shape of the weir, and other things like that, some irregularities in the concrete and so on. So it's better to be conservative and safe and say, okay, it's a few centimeters at least. So for instance, let's say, I don't know, 4 centimeters. It's really very safe. But I know that I have gaugings anyway, so it's not necessary to be over precise here. And the activation stage is 3 centimeters, so 0.03. And here again, I would set 1 centimeter uncertainty because I'm not sure the real work is really as precise as the design was. Okay. Then we have this compute button here. If you push it, then it computes the 3 parameters of the BaRatin equation here. So A, B, C. Here we had different physical parameters that are easier to define than A, coefficient A. So that's why we go through this assistant, because it's easier for us to give the width and the elevation of the weir than directly give the value of the coefficient of the equation, which is this product. You see it's 0.71. It would have been very difficult to guess that. So it's better to give the width and the elevation instead. But the exponent and the activation stage are of course the same as the prior values we set here. So you do apply. You push a lot of apply buttons in BaRatinAGE. It's safer to push any apply button you see at any step. It can be safe also to save here the study. Sometimes it can crash. It's quite unusual, but still can happen. So up, I will save it with another name. Okay. So now we have defined the first control. We have to define the second control, which is the medium weir, the second weir. So if we get back to the design, we see that here it's easier here. Total width is 50 plus 156 centimeters. So total width is 2 meters and 6 centimeters. I will put this here. So again, rectangular weir, prior assistance, up 2 meter 06, 2.06 meters, plus minus, I'd say 10% perhaps, so 20 centimeters. Rather large. I think that the design is more accurate than this, but anyway. And the elevation is you see here 20 centimeters above the datum. This 17 centimeters is actually the length or the thickness of the weir. So it's 20 centimeter high. So here 20 centimeter plus minus, let's say 2 centimeters. Again, I compute the parameters of the BaRatin equation, and that's done for the second control. Third control, higher weir, again rectangular weir, and what is the width? The width is 80 centimeters, and the height is 40 centimeters. Okay, so 80 centimeters, 40 centimeters here. Again, the width, perhaps 5 centimeters of uncertainty, and the height, let's say 4 centimeters. So of course, it would be better to think a bit more about the uncertainty we put here. It's just for the demo. I put some numbers, some realistic numbers, but it's better to compute the uncertainty you can have from your design or from your geometry or your guess. Okay, apply. So now I have written the equation of the curve through the matrix of controls. I have set the prior distributions of all the parameters of the 3 controls, except the offset B, that in this case, B is equal to K. And then I can compute the prior rating curve, say from stage 0. So we saw that Yeah, the highest weir is 40 centimeters high. I think that the highest flow there was about 70 or 80 centimeters. So let's say we want to compute a rating curve up to 80 centimeters. And importantly, I know that the weirs are not submerged. They are still active as controls for this stage. So I'm not extrapolating the model beyond its validity domain. That's a very important point. Of course, I could compute a rating curve up to 10 meters high, but then the bridge would be submerged and the weirs would be destroyed maybe. So that's not a good idea. So here we have some parameters to compute the rating curve. So the range of stage, the number of steps in the grid we want to have. So that's just defining the positions of the stages for which we want to compute the rating curve. And so by default, it's 101, so that we get a stage interval that is the stage range divided by 100. But you can change either the number of steps or the stage interval. And you can convert from each step to n step with this arrow, or the other way with this arrow. And at the end, what counts is the stage interval, sorry. And then run. So it will run the computation of the prior rating. And I think, yeah, it's hidden here. I have this message that's all down. Everything went well. And I have this prior rating curve computed. Prior meaning that I have not used the gaugings yet to calibrate it. This is a specific case where we have a very precise knowledge of the controls. We'll see another case where we get much more uncertain prior rating curves. So here we have the prior curve in black with the prior uncertainty in blue. This prior uncertainty is the propagation of the prior uncertainty we set on the parameters of the curve, of course. And in pink here, we have the activation stages. So remember, it was 3 centimeters for the lowest control, 20 and 40 centimeters. And the pink envelope, the pink band, the pink ribbon here is shows the 95% uncertainty interval around those activation stages. We'll have a very similar display of the posterior results and the posterior rating cloud. There are a few graphical options, like I personally like to display the discharge on a log scale. That is a nice way usually to better see the breaks between the controls. And also it shows you have the same resolution for the low flows and the high flows in percentage of the flow. In other words, 10% of discharge error here for low flows will have the same size as 10% of discharge error for the higher flows over there. So it's a bit harder to read. So that's why we have the two options. You can also keep the linear scale for discharges and zoom in to see some details for low flows, and get back to the initial view by clicking right and dragging upper left, or zoom, the opposite of the zoom option. So you have the two options, and I think this one is good. We don't have a log scale for stages, because stage is not a physical it's not a physical parameter. Actually, it's an arbitrary value compared to an arbitrary datum. It can be negative, so it's not good for log scales. What is physical is the flow depth, so h minus b in the stage equation, in the rating curve equation. But b is different for any segment of the curve, so it's difficult to represent this on the same plot. That's why you always have the stage with a normal scale, and you can have discharge Q in log scale or normal scale. You can plot outside, you can display the legion. So legion, I think in next versions, maybe the legion will be included in the plot, but so far it's displayed out of the plot, but you have the details of the objects you can see on the plots. And you have a few more plots. Yeah, you can see the spaghetti, which is a subsample of the real samples we have behind this prior uncertainty envelope. Okay, so that's all for the prior rating curve. We have done quite a big part of the total work now. Then we have the gaugings. Oops. Oh, sorry, I have not opened the .bar.zip file. I hope you have done so. Or I have not opened the right one. What is the? Do you have the gaugings and the stage series in your files? You should have. Let me check. I will open another BaRatinAGE software. I'll open. Oh yeah. So I don't know why. Okay, that's strange. You should see the gaugings like this. Sorry. I think the quickest way to go is that I just quickly reset the controls. That will be quick. Up. So I think the width was, sorry for that. So 40 centimeters, 3 centimeters. Okay. I'm not sure I put exactly the same value like previously, but try to do it quick. I think it was 3.06 and 2. That's 20, 40. And the last one, it was 80. Oh no, sorry, 40. 40 and 80 in width. Okay. Okay. Sorry for that. So we can compute from 0 to 0.8. Back. Okay. I think I'm nearly the same step. And I will call that okay. So now you should have this prior rating, and you should have the gaugings already in your data file. So to save time today, I provide the .bar.zip file already set with the gaugings. You will see in the manual that it's not difficult to prepare a text file with the discharge measurement data. It's a text file that is very similar to this table, actually, with one line, one row header, and stage, uncertainty on the stage of the gaugings, which we advise to set to 0, because if you define a stage uncertainty for the gaugings, the method that BaRatin will apply is not good. So please keep 0 as stage uncertainty for the gaugings. Then the discharges for all the gaugings and their uncertainty, their discharge uncertainty in percentage of the flow. So here we have 2 more uncertain gaugings for high flows with 10% uncertainty and 5% uncertainty for the other ones. It was estimated by the field hydrologist using tools like, you can use tools like QRevInt for the ADCP uncertainty, for instance, or other tools for current meters or tracer dilution and so on. Not the topic of today. Sometimes when I have not so much time or not so much information on the gauging's uncertainty, I just assume realistic values depending on the measuring technique. So I think it's explained in the documentation in the manual. But typically I use 5% for an ADCP gauging done in good conditions, or 10% otherwise, 15 to 20% for surface velocity gauging, and so on. So we have this set of gaugings. If we zoom in, we can see that they come with uncertainty bars, and we can also display them in log space. And we see that there will be some breaks that are due to the changes in controls. Okay, so oops, that's okay for the gaugings. So we have a hydraulic configuration. We have a set of gaugings, so we can compute a rating curve. So same procedure. Click right, add a rating curve, or click on this, or click on this icon, or click on or go through the menu. So I can give a name to this rating curve. So for instance, I can say, okay, that's the rating curve. The rating curve I compute with a 3 years model and gaugings from 2014 to 2018. And that's the rating curve for 3 years. You can do anything you wish. And you can also add comments in the description tab here. You can put some more explanations. Can be very useful if you get back to your analysis later on, or for other people to understand what you have done. So to compute a rating curve, I have to select a hydraulic configuration. Here I have only one in the catalog, so there is no choice, 3 years. A set of gaugings here, and a remnant error model. So this, we advise not playing with this. I didn't really explain the different models we have for the remnant error. In the vast majority of cases, the default model is okay. So don't bother with this and stick with the default option, the linear remnant error model. And then we push the button apply, and then we define the range of stages over which we want to compute the rating curve. So say from 0 to I don't know, 0.8. the same as for the prior rating curve, and we can run the computations. You may have noticed that you can compute the rating curve for stages that are smaller than the lowest activation stage in the controls. There is no problem for this. The rating curve will be simply yielding 0 discharge, but there is no, the computation still works. Okay, so this is done. So remember the Bayesian magics happened and combined the information we set in the hydraulic configuration, the prior knowledge, and the information we have in the gaugings, considering their different levels of uncertainties. So first, what we can see here is that actually we have virtually no gaugings measured when the highest weir was flowing. So of course, the uncertainty of the third control will be quite high, quite similar to the prior knowledge we had. But as the first and second controls are still active for this third segment of the curve, the uncertainty remains limited because we still use the calibration of the two lowest controls and the information from the gauges. So we can display the curve in log scale for the discharges. It's a good way to check the scatter and the breaks. So you see the clear break in the curve when it goes from the first weir to the second weir, and the third weir is actually small compared to the first two ones, and then there is the break is very small actually. Okay, so the legend, yeah, the legend shows reminds you what are the different things we see in the plots. So the max post rating curve, or posterior here, parametric and total uncertainty ribbons, the activation stages and their uncertainty, and the gaugings and their uncertainty. So you see that compared to the prior rating curve, you will see that the uncertainty of the activation stages, or the crest elevations of the weirs, have been reduced thanks to the gaugings. Now we have only a few centimeters of uncertainty around those elevations. We can also plot other things, important checks. So in more plots here, we can plot the distribution, so the prior and posterior distributions of all the parameters of the rating curve. So you can see, so the first line is for the first control, second control, and the last row for the third control. We have on the left, we have the K parameters, so the activation stages. You can see that actually here the results are very close to the prior estimations, and that makes sense that we have a very precise design of the actual weirs. So when we have gaugings, actually the information is consistent. It reduces a bit the uncertainty, but not so much. And here for the third control, you see that the activation stages has very similar posterior results compared to the prior distribution, which means that there is virtually no calibration using gaugings. And that's what we saw. Actually, there are no gaugings for this range of flow. So you see that for the third control, actually all the prior distributions are very similar to the results. So basically, we only rely on the prior information for that control. And fortunately, it is negligible in the rating curve. But if we had a very wide plot plane, that would be a problem. So we have a fair calibration of the state, the activation stages of the first two weirs, a good calibration of the first, the coefficient of the first weir, some calibration for the coefficient of the second weir. The exponents C are actually very precisely set in the priors based on the hydraulics theory. So it's very usual that the results do not escape from the prior distribution. They stick to the prior distribution. If there is a significant difference, that's another sign of a potential mistake in the model, in the hydraulic configuration. And then we have the B values that are computed by continuity of the rating curve. In this case, we just add new controls. So activation stages are equal to the offsets. And the offsets are equal to the activation stages. So yes, we can zoom in a bit to get the same range here. You see that the distributions are actually exactly the same because B is equal to K. But that would not be the case if some controls would disappear and be replaced by other controls. Then K and B could be different. Okay, so that's an important check. We can also compare the prior and posterior values of the parameters. So that's exactly the same results. But now we just display the central value of the distribution plus minus the 95% probability interval width. So it allows for more precise comparison of the prior and posterior results in terms of numbers. We can also compare the rating curves, prior and posterior. So you see here that we have quite a good agreement. And the posterior uncertainty is included in the prior uncertainty, so that's nice. We can check the MCMC simulation traces, so the iterations of all the parameter values that were sampled in the posterior distribution. So we have this kind of stationary random walk, which is what we like to see, and that's okay. And some spaghetti, not all of them. Usually we keep 500 spaghetti by default. I think we display less than that to better see the scatter, but that's just to illustrate what is behind the pink uncertainty, the parametric uncertainty. That's the scatter of the spaghetti, the rating curves. Sorry. And we have some remarks or some warnings. Yeah, here. So those are some automatic checks of the consistency of the prior and posterior parameters. So that's a bit the same as what we visually checked, but there are some criteria here that are computed just to provide some warnings in case we have something not going right. Okay. Now, what I could do is to test another configuration. So there is no reason to, I could play with only 2 weirs, for instance, but what I will do first, let's imagine that I had a 3 weirs, the same 3 weir model, same assumptions, but more uncertain knowledge of some parameters. So I can click right and duplicate the configuration. That's what I've just done. So I have the same thing here, but let's imagine that for the lowest weir, the first weir, Actually, I didn't really know the activation stage. And I just know that it's around 0 plus minus 50 centimeters. So much more uncertain. And I will do the same for control 2. So activation is about 30 centimeter plus minus 30 centimeters. And same for activation of the 4th. Let's say it's about 50 centimeters plus minus 50 centimeters. And the width could be known just by 50 centimeters. So I artificially increase the uncertainty of some of the prior parameters. So you see that now I recomputed the prior rating curve. So it's much more uncertain than what we had previously, just for a test. And then I can duplicate this rating curve just to compute another one with uncertain priors, or more uncertain priors. So that's just a trick. I could have created a brand new one rating curve, but duplicating the rating curve is convenient because I keep everything constant, but the hydraulic configuration. Here in the catalog, I have 2 options, and I can select the 3 wheels uncertain prior configuration, apply, and run again to recompute the results with the same set of gaugings. So that will come in a second. Where is it? Yeah. Okay. So now we have, so maybe you don't see very well, but if we zoom on the activation stages, we see that the 2 first activation stages are quite well estimated thanks to the gaugings. But the third one is very uncertain because we have no gaugings to estimate it better than what we have in the priors. So we have this very wide uncertainty here that will affect the highest part of the rating curve. And if we just look at the prior posterior distributions, yeah. So you see here for the first control, we had a very flat prior distribution, very uncertain, very vague. But then, thanks to the gaugings, we can have a very precise estimation and very close to the value we had previously. So because we have quite a lot of precise gaugings here for this range of flow, it's very easy for BaRatin to estimate this K parameter here. And also here, the same for the second control. But for the third weir, we have no gaugings, and then it sticks to the prior distribution, which is quite wide, quite uncertain, and there is no improvement of the K and A parameters that were set very, very uncertain. So that's just a way to illustrate what happens and how the results depend on the priors. As well, if I design a silly model, let's say that I tried to represent that compound weir with only one weir, and I will say, okay, it's a weir that is say about 2 meters wide and yeah, say 20 centimeters high. So 2 meters plus minus 1 meter and 20 centimeter high, plus minus 10 centimeters. So of course, it's not a very good model for such a control. So let's compute the prior rating curve. Okay. So we have this kind of prior rating curve. And now I can compute a third rating curve with this poor model. So let's duplicate rating curve for one weir model in the same gaugings. Okay. So I select the one weir model, same gaugings, apply and run. And then I expect that I'm getting into some troubles. So it tries to find the best calibration, the best adjustment possible. You see that it sacrifices the low flow gaugings here. It has to increase the remnant uncertainty because there is a large deviation between the model, the curve, and the gaugings here. So that's not a good sign. And if we go and have a look at the parameters, yeah, actually there is no, that's not here that you can see the problem, because actually the posterior distribution and the prior distribution are quite consistent. Then for this situation, you see the problem from the large scatter between the data and the model. Another illustration would be, and that would be the last one, if we use some biased priors. So now I have the right model, 3 weirs, but let's imagine that I have not the right crest elevation for the second weir. So I assume that it is at 10 centimeters instead of 20. And I'm pretty sure of my guess. So plus minus 1 centimeter or plus minus 5 millimeters. Okay. So then I have this kind of prior rating with the quite precise stage for the second control. If I just recompute a curve with this model and the same gauges. So 3 weirs biased, I run. So I expect that we will have a conflict between the priors and the posteriors in such a case, because we have enough gaugings to estimate the second activation control stage. And so first symptom, we have large deviations between the gaugings and the curve. Not good. And here, yes, we see that my prior knowledge on K2 was biased, but actually it's not here that we see the problem. Due to some correlation between the two parameters, it actually destroys the results of A2 because there is more freedom. Here, the prior is very tight. So it's difficult for him to escape from the prior distribution. It's easier to escape from the A1 and A2 prior distributions, which are actually good, but it has to escape from the prior distribution to try to find the best solution he can. But here, clearly, here we have a conflict between the prior and the posterior distribution. So that's something that should push the user to review and question his or her first assumptions. Okay, last thing we can do is to play with the stage records now. So we have this stage series already imported. So again, there is a format to follow to build a text file. So you can import the dates, stages, and the uncertainty on the stages. So we have two kinds of stage errors here. The first column, UH, stands for uncertainty due to independent errors. So from time to time, you have totally independent stage errors. For instance, due to the sensor precision, due to waves, due to any perturbation that does not last over time. But here we didn't use the two last columns. They can be used to define periods of times. And for each period of time, you can set an uncertainty that relates to a constant error. So that's more used for reflecting the error we have in the calibration of the recorders, of the stage recorders. If you calibrate it at a given time, you can assume that between your field visits, you have a small unknown error, and that uncertainty here can reflect this kind of uncertainty due to constant errors. I just closed the comments here, but here we assume that we had a plus minus 1 centimeter uncertainty on the stage records, and here the uncertainty is not displayed. And then with a rating curve and a stage record, we can compute a flow series, a discharge hydrograph. So I will compute year 2014 with the 3 years rating curve. That's my code. Okay, and we just have to run it. So yeah, you have a warning message informing about the expected size of the file and the expected no, just the expected size of the file, just to warn you, because when you have very dense stage series, very long ones, it can last for a while, and it can also create quite large data files. So we have now the discharge time series corresponding to the stage series, and with the uncertainty corresponding to the stage records, so the plus minus 1 centimeter error or uncertainty, sorry, that creates this discharge uncertainty in yellow, and the parametric uncertainty of the rating curve in pink, and the total uncertainty in red, combining the stage, parametric, and total uncertainty. Okay, so we still have to improve the display. You see the time is displayed in years, in fractions of a year. So that's something we plan to improve in future versions. Also importation of data and some things. You can export pretty much everything. For instance, the flow series, if you click right, you can export the values, and then you get a text file with the time in the first column and the values of the main flow series in black, and the values, the lowest and upper bounds of all the uncertainty intervals we can see here. And the same applies to rating curves. If you click right, you can export the values. So everything that is used here to create the plots, you can create it in your favorite software and modify it. You can also export the equation of the curve. So that's a new feature that was asked by many users actually. Let me see where it is. No, it's not here. Okay. Okay, so oops, doesn't want to come. Yeah, it looks like this. So it's just a text file with the different equations that are used for the max post rating curves with the values of all the parameters. If you want to include this equation in another software, for instance, you have the equations and the values of the parameters for the max post, only the max post curve, max post rating curve. And you can also export the MCMC simulations, so the traces or the samples of the parameters if you want to play with it and with them and make some statistics on them. Okay, so we're done for the Mercier case. I hope some of you have followed and made the same computations. I still don't see the chat, so yeah, maybe there are some questions, but I think Ben has answered everything. Yeah, I think so. Okay, yeah, so many questions. Great. Okay, so let's do the last exercise now. So we're done with Mercier. So the other file you can import in BaRatin is the Meras station example. So this river flows in the southeast of France in the Mediterranean region. And that's a station we have studied for many years. It's quite nice rating curve here, and many rating shifts actually. Each time we have a flood there, the riverbed degrades more or less strongly, and it results in rating shifts after each significant flood. So you have some numbers. The station is installed under that bridge over there, so you have a low flow view here. You can imagine that during floods it will flow above the banks in the floodway as well. So you have a top view of the ridge, the simple ridge, no tributaries, no backwater effect. Staff gauge on that bridge pier. So first, same exercise. We don't have artificial controls here, but still we have to identify the main controls that will make the rating curve. So for low flows, for intermediate flows, for high flows, for the whole range of flow we want to model. So from pictures, but or from the field visits, which is better, of course, we can identify some controls. Maybe you can guess some of them, but very typically for very low flows, the stage discharge relation is controlled by a weir, a natural weir, I'd say, some riffles over there. So here it's like a pool. It's very flat, very horizontal water profile. And we have these stones over there creating a small fall. But actually, if some swimmers or some kids just drop some new stones over there to increase the depth of their swimming pool, they can significantly change the rating curve up here. So the low flow critical section is around there. Then we have, of course, a main channel control in the main channel for intermediate flows when all these faults over there are disappearing. And floodways, we have floodways on the left and on the right sides of the main channels. With some vegetation in that floodway, geometry that is not very simple, but we will represent it with a rectangular channel control as a first guess. Remember my philosophy of modeling rating curves. I tend to start with the simplest model I can imagine. So yeah, the model of control will be like this. Control 1, this natural river over there, which is oblique actually. Then the main channel control, so section control 1, channel control 2 for the main channel, and channel control 3 as a combination of the two floodways, right and left. So that makes this typical matrix of controls, which is pretty much the default matrix I use for most of the stations I have in this kind of configuration in the field with natural controls. It's very often I have this this kind of 3-segment model, very common. Okay, what information can we have? So we have a cross section. It's a bit, yeah, it's 14 meters downstream of the gauge, so it's around there in the pool. So we must be careful that it might be not exactly representative of the specially averaged geometry of the channel upstream and downstream of the gauge. So the extent of the controlling channel is not always very easy to assess. We have to imagine the maximum, the longest channel over which some geometrical modifications will affect the stage discharge relation at the gauge. So that's sometimes difficult to assess without a hydraulic model. Of course, if we have a, say, a 1D or 2D hydraulic model, then it's easier to identify from sensitivity tests, for instance, the length, the extent of the controlling channel. So we will use anyway this cross section to have an idea of the width and depth of the main channel, the activation stage of the floodway, and the width of the cross section. So time is running, so I will jump to the results actually, but you can do the exercise if you wish. I will provide the slides as well. Yeah, the staff gauge datum is this. So this allows you to define here the width of the main channel. The slope is given as well. It's usually a parameter that is not very easy to guess precisely. The roughness of the channel. So I usually use 25 as a default value for the Strickler coefficient, 25, 30 for larger streams, larger rivers. In the user manual of BaRatinAGE, you will find some help, some tables, classical tables or equations to estimate Strickler coefficients or Manning's N coefficient for a given river. There are some catalogs with pictures or formulas or some questionnaires to help you have some values for the friction coefficient if you don't have some expert knowledge of this. And K2, yeah, K2 is the activation stage of the floodway that we can also estimate here from the cross-section survey. Okay, and as we have a vegetated floodplain, we assume a lower Strickler coefficient, which means a higher Manning's N coefficient for a rougher bed due to the trees and bushes we have there. So we have quite an uncertain width, uncertain slope, and quite uncertain activation stage of the so over bank flow level for the floodway, for the floodplain. For the first control, it's more difficult to guess. From the field visit, we had quite a rough estimate of the width and very rough estimate of of the activation stage of the weir. So remember that for the main channel control will replace the low flow section control here. So here K2, the activation stage, is not equal to the elevation of the bed of the main channel. It is the water level above which the main channel replaces the low flow section control. So in other words, it's the water level for which the weir here, the low flow critical section, is submerged and no longer active. So beware of this. Then the floodplain, we add this control to the others. So K3, the activation stage, is equal to the offset B3. So that's the simplest case where K3 is equal to the level of the bed of the floodplain. Okay, so I can use these values to create my BaRatin model. So if you have the software, maybe you have already opened the meras cp.bar.zip file. So here again, we have already gaugings. So we have gaugings for two different periods of time because we had a rating shift. We had actually several rating shifts. So for those two periods, we would like to compute two different rating curves. We have a stage series, 2001, 2008 for the first period. So again, now you know the method, so I will go a bit quicker. We add a hydraulic configuration with 3 controls. It's not a very good name, but so we'll have the control 1 for low flows, so active for low flows, the riffle, the weir. Then we don't take this box because it will disappear and it will be replaced by the main channel control. And then we tick this box because for the highest, the upper segment of the curve, we'll have both control 2 and control 3 that will be active, the main channel and the floodplain or the floodway. Okay, so I define the low flow section as a rectangular weir. I don't really know precisely its shape, but I remember that I estimated the width to be 8 meters plus minus 4, so quite large uncertainty. K1, the activation stage 0 plus minus 1, so basically I have no idea of the value. Control 2 is a channel control, rectangular channel for the main channel. So I said Strickler coefficient of 25. You can also use Manning if you prefer here, and it will convert to the Strickler coefficient. Or also in the options of BaRatinAGE, you can switch to Manning's N by default if you prefer to use Manning's N instead of Strickler coefficient. So plus minus 5, yes. Width is 15 plus minus 5 meters. Slope is 5 meters per kilometers. So be careful. The slope here again has no units. It means that it is defined as in meter per meter. So not in meter per kilometer. So it should be very small values like this. And activation stage, no idea again, so 0. I guess it's near the datum of the staff gauge, but plus minus 1 meter. And remember that we have rating shifts happening at this site, so it's better to have quite a large uncertainty in the priors, so it can be calibrated using the gaugings for each period. Okay, so that was the main channel. And control 3 is the floodway, or the combined two floodways, modeled as a rectangle. Oops, sorry, not a rectangular weir, but again, rectangular channel. Yes. The strickler is now 15 plus minus 5. The width is 30 meters plus minus 10 meters. Slope the same as the main channel. And activation stage is the elevation, the mean elevation of the floodway compared to the main channel. So 1.2 from what I saw in that cross-sectional profile, plus minus 0.5 because it's quite uncertain. Okay. So I can compute the rating curve up to I don't remember, maybe 4 meters. Let's say, oh, sorry, I made a mistake somewhere. So 1.3. Yeah. You cannot define the same activation stage for successive controls. That's something that is forbidden. So I have to say it is a bit higher, maybe 10 or 20 centimeters above the level of the weir, because of course the weir cannot instantly disappear as soon as it is activated at level 0. It cannot be replaced by the main channel at the same level or for a smaller level. So the activation stages must be increasing from control 1 to control 2 to control 3, at least the central value. Okay, should work now. Okay, so I have this quite ugly prior rating curve, but nothing to be scared of. It's the reality of my knowledge, especially for the low flow controls. I have very little information. And I will compute two rating curves now. The first one for the first period, so 2001-2008 rating curve. Yes, so my three control models, sorry. The gaugings for the first period, so that's okay. And let's compute from 0 to 4 meters. Maybe it's a bit more than that. I don't remember exactly the full range of stages we have. When it's finished, I will have a look at the stage series. Yes, okay. So in the stage series, yeah, okay. Yeah, it's nearly 4 meters for the highest flow, so that's okay. Okay, so I have this result. It looks good, actually. You see, that's typically what I like. The remnant error is quite small. It's the parametric uncertainty is dominant, except maybe for low flows. Okay, here we have some ugly thing. Actually, the rating curve is computed down to the lowest gaugings, but we ask only down to 0 meters. So I will compute the rating curve a bit lower, so we can see what happens with the lowest flows here. So of course, when I set the discharge in log scale, we see that the uncertainty increases. Yes. Okay. So here we have quite a large uncertainty in percentage of the flow, of course. In cubic meters per second, it's quite small. But then the remnant uncertainty is higher for low flows because there is more scatter of the data around the curve than for high flows, and especially for the extrapolated upper part of the rating curve. It's dominated by the parametric uncertainty because we have very few gaugings and we rely on the prior assumptions we made on the controls, which is something dangerous. We have to be careful with that. We have no gaugings to check for our model here. So we have to be careful with the uncertainty we set previously. But here again, we have the main channel and the floodplain both active for the upper part of the rating curve. So the information coming from these gaugings there for intermediate flows, they bring information on the main channel control that is used for the upper part of the curve. So that limits the uncertainty. Let's have some checks. So you see no conflict between priors and posteriors and results. Here, very flat, very uncertain guess for activation stages, but the gaugings bring enough information to get a quite precise idea of the activation stages. And the coefficients, we had quite uncertain slope estimates and width estimates, but at the end of the day, the gaugings are able to reduce the uncertainty, and it's still consistent with our prior guesses. Here you see that so K1 and B1 are the same, but K2 and B2 are different. Okay, so the level of the riverbed is near 0, whereas the activation stage is around 20 centimeters. So that's the water level above which the section control is replaced by the main channel control. Okay, so that's enough. And so we can compute another rating curve for the other period of time with the other gaugings. So 2011, 2014. So here for this new rating curve, I keep the same model. I only have one actually, but I select the second set of gaugings for the second period. Apply and run. So you see here that the new gaugings are clearly above the previous rating curve, which means that the bed has degraded. Okay, and I have this new fit. So again, parametric uncertainty in pink is dominant. Again, K1 and K2 have been estimated nicely. So it's still lower. Let me compute the rating curve down to 0.7. Okay, just to have the rating curve down to the lowest levels. It's a problem. After a while, you have to rebuild a new staff gauge down and down. Okay, so now I have the lowest end of the rating curve. If I have a look in log scale, yeah, we'll see that the uncertainty increases, but it's smaller than for the previous period. Certainly because we have more gaugings and are more better aligned along the rating curve. We can check for no conflict. Again, a very good fit, whereas my prior knowledge was very flat, very uncertain. There is no real way in BaRatinAGE to overlap two rating curves for comparison. So that's something you have to do outside of the software, just by exporting the data, exporting the values, and you can plot the two rating curves in a spreadsheet or another software. That's maybe something we will propose in future versions. So yeah, just to illustrate that in BaRatinAGE, you can use and test several hydraulic configurations, several sets of gaugings, several stage series. Here we have only one. Actually, and in this stage series, we have defined the uncertainty due to random errors here, but also you can see periods of time, 35 and 36, maybe other periods, 37, 38. That corresponds to recalibrations of the data logger, of the stage recorder. And then we have a 1 centimeter uncertainty reflecting a constant stage error over those time periods. So I have two rating curves. Of course, if I want to compute the 2001, 2008 flow series, of course I have to use the 2001, 2008 rating curve and not the other one. Okay, but so far that's the only way you can cope with rating shifts in BaRatinAGE. In next versions, we hope to implement the SPD method that was developed in the PhD of Valentin and Manzanares. And this is a nice model that computes a family. It's a single model computing a series of rating curves over several periods. So you deal with a single model, and in addition to the prior information on the controls, just like in BaRatin, you have also to set prior knowledge on the rating shifts, the possible changes of the bed. Okay, and then you have this type of results. If I zoom on a flood, I have again the most likely discharge values in black and the uncertainty intervals here dominated by the parametric uncertainty for high flows. Okay, I think I will stop here with this example. I won't explain some tricks we have when we want to compute a series of rating curves. There are some possibility of reusing calibration results from the previous period. And then, so this kind of values here. Imagine I have calibrated the rating curve for period 2 here, and I want to compute the rating curve for the next period. And I know that only parameters K1 and K2, so corresponding to an erosion of the bed, no change in the width, no change in the roughness. So I decide that only the elevation of the controls, of the two first controls, has potentially changed. Then I will keep the same posterior values here as the prior values for my next period, except for the uncertainty of K1 and K2. I will keep them large enough to be recalibrated with the new gaugings I have for the next period of time. So I have no time to explain the details of this, but that's a procedure that can be used with the current version of BaRatinAGE to transfer some information from one period to the next when you have some rating shifts. But the best method would be that SPD method we have here. This yeah. So when we have some rating shifts here, so that's the Ardèche at Meras, same case. You can see that the shifts are visible in the stage time series. After each significant flood, we have a drop in the base level of the stage hydrograph. And if you look at the gaugings here for the same periods, same colors, you have a constant shift of the rating curves from from right to left, and which means decrease in the bed level. So that SPD model I was talking about is hopefully the next model we will offer in BaRatinAGE. We have to adapt the interface a little bit to do that, but still in the next version 2.3, that will be issued in the next month, before the end of this year, I think. You will see no difference, same BaRatin model, but the engine has been changed to BAM instead of BaRatin. And BAM is an extension, a generalization of BaRatin, which can estimate a wide range of models, not only BaRatin. BaRatin will be one of the models, but we will be able to propose other models, other rating curve models, including SPD for rating shift, a hysteresis model using the Jones formula, and other models. But the first one, we think the most useful for users will be this one. But of course, for these models, you need to set the times of the shift. So they are supposed to be known. And we also have other tools to estimate the shift times, to detect the shift. But that will be another tool and another story. Okay, I finish here. I pretty much presented the main things I wanted to present you today. I hope this will help you. I hope it was informative. And if we have some questions, I can answer quick questions before we end the session. Just turn back to the chat to see if there are some questions. I saw that Ben has answered many questions. Thank you, Ben, for that. Okay, so I start with the last one. When identifying the structural controls, is there a cutoff point or rule of thumb with distance downstream from the gauge? Oh, yeah. I have no real rule of thumb. There are some rule of thumbs when you want to install a gauge upstream of an artificial weir. I think it's something like at least 3 times the flow depth over the weir or something like that. But the question is different. Now, again, we have to imagine that if we change something at the cross-section, the critical cross-section, that will impact the stage at the recorder. So sometimes we just try to imagine it. Sometimes we have a hydraulic model, so we can do some sensitivity tests. And for sure, the flatter the stream, so the lower the channel slope is, the longer a section control can influence the station. So sometimes I have some examples of stations with several kilometers between the gauge and the weir further downstream. And for low flows with a very flat, very mild slope channel, we can have the influence of the cross section. And also the influence of the section control can disappear because the fall disappears, because the weir is submerged. But in other cases, when the discharge increases, the influence of the weir is repelled further downstream, and in some cases downstream of the gauge. So sometimes you have the fall is still here, the weir is still active, but its influence is repelled further downstream, and then the gauge is not influenced anymore by the weir, and you shift to a channel control. But I have no clear rule for that. Yeah, to detect shifts, actually, if you're interested in that, we propose a segmentation procedure. We're still working on it to stabilize the procedure, but we can share tools that we can apply. So those methods are derived from another PhD work by Matteo D'Arienzo, and he developed several shift detection tools. One the best one, in my opinion, is the tool for segmenting the residuals between gaugings and the basis curve. So that tool is available. There is a paper actually on that method published. We also developed methods for detecting shifts from the stage record. So from the recession, you can extract from the stage series, and you can see that when the flows goes to 0, the stage tends to different levels, and then you detect that the bed has changed and there is a rating shift. So and there is a third tool based on an estimation of the bed load transport over the flood events. So we could, if you're interested in that, please contact us and we can share some things. What about Maxime's question? Okay. David, okay. I think, are there some other questions, or I think Ben has answered the other questions. Yes. Okay. But I will save the chat as well and review it later. Okay. No other questions? If so, okay. So as I said, I will provide the presentation, and so on the YouTube channel of the Groupe Doppler Hydrometry, so the French-speaking hydrometry network, for replay, and also I can provide the slides. So if you don't find them, just leave me a couple of days to release that. But after that, just feel free to contact me, and I can share the slides and the video and so on. And of course, if you have other questions, feel free to ask and contact me or the BaRatin.dev email list. Yeah. Just say hello. Yeah, I say Pankaj. Hello to Pankaj and to the large group of Indian participants. It's very nice to see you. And yeah, if you want to have other languages again, just feel free to ask and translate. We can have languages.
Informative presentation. Very complex topic.
Oh, sorry, I hardly hear you, Pankaj. But yeah, I will increase the sound.
Can you hear me now?
Yeah, it's better. Yeah.
Thank you for preparing very informative presentation on a complex topic. And from India, normally we do not express our discharge with associated uncertainty in our publications. So all this was an kind of eye-opener for participants from my organization, Central Water Commission, and definitely it enlightened us that measuring discharge and expressing it and using it in different scenarios and particularly providing the associated uncertainty with those measurements is so much important. Thank you. Thank you from all of us.
Okay, thanks, Pankaj. And yeah, in France, we have many services applying this method or other methods actually to compute the uncertainties. But so far, they are just used internally. They are not released in the National Archive. That will be a next step we plan to jump in the coming years. But uncertainty is now increasingly communicated and used for decision makers and flood forecasters as well, but internally in the governmental services. And But in the future, the French service plans to release the uncertainty with the data as well for any data user. I really think it's important because as we release our data very widely now through internet archives and so on, we cannot imagine all the uses of our data that can be done. Some people, for some uses, it's good to have a 20% uncertainty, no problem. And for other decisions, some people expect very small uncertainty that we cannot reach, like 1%. So it's important to communicate on this. So the duty is not on the shoulders of the data producers, but on the data users and decision makers. So that's also a motivation for that. Yeah. But thanks again, and yeah, I hope we will have some discussions on that later on. I think I need a beer now, but I talk too much. But yeah, feel free to contact us and ask questions or make suggestions to improve the method and the models and the software. Sorry, because that's really the way we built the method for. We have built the method for more than 10 years now, thanks to the feedback of the users, both students, academic users, and operational agencies in hydrometry. So feel free to really to give any feedback. Will be welcome. Thanks everyone. Sorry for the late time, especially in India. It must be quite late for you guys. And yeah, see you later. Bye-bye.